next speaker, John Danloe, burn severity trends and elevation, a temporal analysis from 1984 to 2011 in Arizona and New Mexico.
Well, good evening, everyone. My name is John Danloe, and thanks again for being here tonight for all of our presentations. Tonight, I will be discussing burn severity trends and elevation in the states of Arizona and New Mexico between 1984 and 2011. Now, prior studies have taken a look at burn severity and its connection with total area burned. Holden paper in 2007 and another paper in 2011 by Dillon each took a look at this, and they found that typically in the Southwest, when there were larger fires, there also tended to be a higher proportion of moderate burn severity and high burn severity in those fires. Now, why is that important? Let's find out. These two pictures here, we have the Rodeo Chestnut Fire of 2002 and the Wallow Fire that burned in Arizona and New Mexico in 2011, are each prime examples of what high burn severity is. High burn severity sounds bad, but when you actually see pictures of it, it's much, much worse. In these pictures, we see high percentages of crown kill in the forests. Seed banks can be destroyed due to these types of fires. Soil can be sterilized because of this type of fire. And also when the monsoons come into the Southwest later in the season, it can cause serious issues in terms of erosion, hydrological and watershed issues, and implications like that. So it's important to take a look at burn severity because it can cause issues like I just mentioned to happen. What I'm going to be taking a look at in my study is the connection between burn severity and elevation on an annual scale. The big question here, what I'm looking at is, are fires burning at higher elevations as the years progress? If we can figure out if there is some kind of upward trend between burn severity and elevation on an annual scale, then we can try to determine what driving factor or factors might be causing this to occur. And if we can isolate what those factors are, then we can try to figure out, well, what kind of future problems and implications might this trend cause. Might not be totally clear, so I've got an image here. Let's pretend that this is my study area. This mountain on fire is my study area. Each year there's going to be a different minimum elevation burn, a different maximum elevation burn, and a different average elevation burn. What I'm looking to see is if over the span of years that I'm studying, not necessarily year by year incrementally, but over the span of years, if there is an increase in the minimum elevation burn, maximum elevation burn, and average elevation burn. And I do this by taking a look at low burn severity, moderate burn severity, as well as the previously mentioned high burn severity. So before I go right into the data that I needed to use to make this study happen, I wanted to give just a really brief overview of the physical geography in my study region. So between Arizona and New Mexico, we have one of the most diverse geographic regions, if not the most diverse, in the United States. Starting down in the Sonoran Desert, we have vegetation communities with saguaro cactus, like I think we're going to hear about later tonight, jumping cholla, ocotillo, mesquite box, all kinds of shrublands. But when you move just a little bit further north, we have the Mogollon Rim, which contains the largest contiguous stand of ponderosa pine in the world. And just to the east, we have the Rio Grande Rift, which over millions and millions of years, kind of similar to the Grand Canyon but on a smaller scale, this watershed has cut through from north to south New Mexico, leaving a really interesting landscape, geologically speaking. And then just to the north, we have the southern Rockies with mixed conifer forests, subalpine species, and mountaintops that are accustomed to having snow on their peaks for several months out of the year. In terms of elevation, the lowest elevation in my study area is 20 meters in the Sonoran Desert. And then up in the Sangre de Cristo Mountains of the Southern Rockies, it gets up to over 4,000 meters in elevation. For those of us that don't speak meters, that is just over 13,000 feet in elevation. So very diverse in terms of vegetation communities and elevation. And in case you're wondering, fires have burned in each one of these different regions that I outlined between 1984 to 2011 to the tune of over 4 million hectares in that span. So there's been a lot of fire in Arizona and New Mexico over this period. So for data, I needed 3 different flavors of data for my study. First, I needed to have elevation data, which I was able to get through the USGS NED data set, which provides 30-meter spatial resolution data for elevation. In this particular image, we see that lighter pixels indicate higher elevation, and the darker pixels, like in the southwest corner here, lower elevations. Second, I needed to have burn severity data, which I was able to get from the Monitoring Trends in Burn Severity project, which provides, again, 30-meter spatial resolution data. And for all of the fires in the western United States that burn over 1,000 acres in burn area, MTBS provides a variety of different files and rasters to kind of catalog all of those different fires that occur. For this study, the main file, the main raster that I needed to use was their burn severity classification file, which is created through a variety of processes, but the main one that they use to create these rasters is called the difference normalized burn ratio, which creates different threshold levels to determine what the different burn severity pixels are based on pre-fire conditions and post-fire conditions. Here we have the Rodeo Chest Sky Fire of 2002 in Arizona, and as you can see, there is a fairly high proportion of high burn severity in this fire. And again, we also have the other 3 burn severities that I have, low and unburned, low burn severity, and moderate burn severity. And to complete the study, I needed to have climate data, which I was able to acquire from the PRISM Climate Group. I used 4 different climate variables for the study: mean precipitation, mean maximum temperature, mean minimum temperature, and average mean temperature. Prior studies for wildfires in the Southwest determined that antecedent precipitation, meaning precipitation that occurred in the last several months prior to the fire season, as well as the temperature of the immediately preceding months prior to the fire season, were both good indicators of what type of burn severity might be observed during that fire season, and also possibly the total area burn for fires. So going off of that, I included that information in my study, and I used these specific months listed to comprise those variables. Here we have the Rodeo Chest Sky Fire again, and what you see here is the mean temperature in 2002. Darker red pixels indicate a higher temperature Celsius, and the lighter pixels are a lower temperature Celsius. So a lot of steps went into making this happen. I'm not going to go through all of them because I don't want to put everyone to sleep. So I condensed it down to 2 main steps that I took to accomplish this analysis. First, I needed to determine if there were trends in burn severity and elevation for my study area, and to do that, I used a tool called Combine in the ArcGIS software suite. What this does is it takes 2 different rasters that have different types of data, and for lack of a better term, I bet Ezra's going to hate this explanation, but smashes those 2 rasters together, creating a new raster with unique values for the possible outcomes from those 2 rasters. Clear as mud. But basically, what it meant for my project is that I took the elevation values, DEM values, and the burn severity values from MTBS for each individual year, used the Combine tool, and it gave me a raster that for each individual pixel burned, I had a burn severity classification and also the elevation at which that pixel burned. From that, I was able to go into Excel, extract some time series values for analysis. Second, I needed to compare those values with my climate-derived time series values, both for each individual year as well as 30-year normals for my entire burn area between 1984 and 2011. From that, I was able to continue the analysis. So before I hop right into the results, What you see here are all the pixels that have burned in 1984, both with the severity at which they burned and the elevation. For 1984, we see the maximum elevation burn is 2405 meters. And what we're seeing, oops, let me start this over again. What you see here, there we go. What you see here is a time lapse of each individual year between 1984 and 2011 and all of the pixels that burned during that year. And what you might be observing is as the years pass, those pixels are shifting further and further to the right or greater elevation. And as we get into the early 2000s, it's becoming pretty apparent that that maximum elevation burn is eclipsing 1984 pretty consistently. Into the late 2000s, and we get into 2011, and we see that there's definitely a difference there. Again, here's 1984, the maximum elevation burn. Here's 2011, and the maximum elevation burn in 2011 was 3644 meters. That's a huge difference between 1984 and 2011. That's just a comparison between 1984 and 2011, but it's pretty obvious in the time lapse that I just showed you. There's a definite shift towards higher and higher elevations. And that animation you just saw pretty much mirrors what I was able to take from my time series values. Here we have maximum elevation burn, and as you kind of see, looking down towards the years, the elevation is burning higher and higher. Not necessarily year by year, but over the span of the years, there's definitely an increase there. We see the same thing for mean elevation burn by severity. Again, as the years progress, the elevation burn is getting higher and higher. So we've established that there is a relationship there. As the years progress, elevation seems to be burning higher. I'm drilling it into you guys. So now we compare this data with the climate variables that I was able to process. Here we have the mean elevation burn by severity with the correlations with the 4 different climate variables I used. Fairly high correlations in the moderate burn severity and slightly lower in the high burn severity. What you see here is the mean elevation burn, again plotted. What those blue bars represent are the departures from the 30-year normals for the mean temperature. So each individual year shows how different that temperature was from what the 30-year normals are from that time period. And what we see is that in years where there was a higher average temperature, we tended to see a spike in the elevation burn, and the severities went along with that spike. Notable years here being 2000, 2002, and 2006. On the other side of the coin, when there was a lower average temperature, this didn't happen for each individual year where there was a lower temperature, but in general, if there was a lower average temperature, we would see a dip in the average elevation burn. Here we have the precipitation departures, and what we see is that in years where there was a lower average precipitation, we would also see, again, a spike in the elevation burn and the severity going along with that spike. And a slightly less noticeable connection here. In years where there was a higher average precipitation, there tended to be a dip in the elevation burn along with severity. So what do we take from all of this? First, I found that there is that elevation burn in the Southwest is increasing on an annual scale. Again, not necessarily year by year, but over the span of years, there's definitely an increase. And second, the climate has been identified as a driving factor contributing to that increasing elevation burn. So among other points we can take away from this, I've outlined three. First, if this trend continues, we're going to see increasing high burn severity in upper elevations. A lot of these upper elevation forests aren't accustomed at all to this sort of shift in climate that we're seeing. They're not built to have small surface burning fires. They have a lot of fuel, and when fire does get up to them, they're going to be moderate and high burn severity fires, which, as I mentioned earlier, is going to have lots of different ecological hydrological and watershed implications, as well as social stability impacts for the people that live in these areas, that have economic interest in these areas, as well as recreational opportunities. A lot of these could be wiped out. And I hate to leave everybody on a really down note, but again, if this continues, upper elevation forests can be vulnerable to, for lack of a better word, elimination. If this type of trend continues, we could see these types of forests disappearing. Again, sorry to leave you on a down note at the end of my presentation, but the data kind of speaks for itself. So, thanks again. If there are any questions, I'd be happy to field them. Thank you very much.
Sorry. Do you feel like precipitation or climate is more of a factor, like to where if we were to get more rainfall, that would be better than temperatures kept going up, or vice versa?
That's a good question. I mean, I'm not an expert in what I'm about to say, but I would guess that those two things are kind of interlocked. I mean, based on this study, they seem to be fairly analogous. They're both affected. They're both affected with elevation.
Thank you, John.
Thank you.